Welcome to our lecture on 4.5, which is all about graphing, which we haven't seen yet in trigonometry, but we're only going to be focusing on the graphs of the sine function and the cosine function. So all the rest we'll handle in the next section. Now, on the notes in front of you, I have a bunch of graphs. This is what you're looking at, and it's overwhelming, right? So we're actually going to take a step back, and I'm just going to do a tiny sketch of something that we dealt with a ton last semester, right? Quick sketch, 0, pi over 2, pi, 3 pi over 2, back to 2 pi, right? So the unit circle. So why the unit circle? Well, because that's where all these graphs are coming from. So let's take a look at the unit circle. And I just want to talk about sine in the unit circle. So if we're looking at the graphs below us, these two over here on the left are examples of the sine function being graphed, and we're just going to kind of relate the two. So we're talking sine for the unit circle. That's analogous with talking about our y values, right? So on the x-axis, sine is 0. On the y-axis, sine is either positive 1 or negative 1. And then it holds values from 0 to 1 and then back to 0 again, right? And it does that on every single rotation. So let's start at 0. At 0, what is sine? Well, sine is 0. And that's exactly what we're seeing on this graph, right? We start at 0, 0. So it's matching up. So as we make our way up to pi over 2, so here's pi over 2 on the graph we're looking at. On the unit circle, as you make your way to pi over 2, sine eventually becomes equal to exactly 1. And we see it's holding that value of exactly 1, and it's building up to that on this graph. Well, as we kind of continue in this rotation, right, we make our way down to pi, and when we do that, sine drops back to 0. But as we work our way down to 3 pi over 2, we don't get sine is equal to 1, we actually get it's equal to negative 1, and that's exactly, as we follow this curve at 3 pi over 2, we end up at negative 1 for sine. And then we do that last little bit of transition, right? We make our way back to 2 pi, and sine of 2 pi is the exact same as sine of 0, which is just 0. So from 0 to pi over 2, we jump up to 1. From pi over 2 back to pi, back to 0. From pi to 3 pi over 2 down to negative 1, and then back at 2 pi, we end up back at 0. So that one rotation on a unit circle is exactly what this darkened in little piece of this graph is, and that's representing the graph of sine. Now, a few things else going on when we look at this, right? That graph here seems to kind of keep going to the positive direction, also to the negative direction. This sine curve, is also called sine wave, it actually just goes on repeating forever and ever and ever and ever. And why is that? Well, that's all from the unit circle again, right? From 0 to 2 pi is one full rotation, but we know we can keep doing rotations. So we can go to 4 pi, 6 pi, 8 pi, and so on. And that is that graph just being repeated as if you do just copy paste every 2 pi. So if you can graph one rotation of that sine, then you've pretty much graphed it completely because you can just continue that exact formula. Now, separately, if we're talking cosine, cosine starting at 0, cosine started at 1, as it does here. And then as you go to pi over 2, cosine goes to 0. So you have something slightly different. Cosine of pi is negative 1, cosine of 3 pi over 2 is 0, cosine of 2 pi is back at 1. So where sine started at 0, 0, goes up, dips down, comes back to 0. Cosine starts up at 1, dips all the way down, and comes back up to that starting point up at a value of 1 again. And again, for cosine, we could keep doing full rotations on that unit circle, and it's going to continue that shape. Now, a few different things on terminology when it comes to this. One is we don't call them full rotations necessarily. That full rotation, and we touched on this last semester, we call those periods. So a period is how long it takes from sine to kind of hold all of its values and get back to that same place. And we know that if you have the sine of 2 pi, that's the same as the sine of 10 pi or 30 pi because they all have that period of 2 pi. So you can remove those rotations out of there. Same thing happening here. That one original sketch of the graph we call its period. And it's how long it takes for the entirety of the graph to get one original piece before you can then kind of copy paste it down the way. Another piece of terminology, granted there's more we'll get to, but just for now is if you look, although it is just the x-axis, you see that we're just kind of bouncing around that x-axis, right? We're going up to 1, then we come back down, down -1, and up to 1, and down to -1, and we are constantly bouncing back and forth between that x-axis. And the line we do that, we call that the equilibrium. So that equilibrium is where we're kind of zeroed out. So that means we're going away from it, we're building up, we come back to equilibrium, we go down the -1, back to equilibrium, and so on. Now, we do have these 5 key points, which are nice. I'm not going to be pushing so much on you identifying the maximums, the intercepts, and stuff like that so much. It's more about getting the shape of this graph down for now. But there are some really good points to pay attention to of just talking graphing. When it hits the x-axis, we know those are intercepts. We know what a minimum and a maximum is, relative in this case. And this is, again, just breaking down the period. So halfway through it, that's half the period. Then you get the other half, so one full rotation again, that full period of it. But we're not going to get into the nitty gritty of forcing you to identify each of those pieces. That's just there to help you. So before you guys are getting all the tools to graph them yourself, I'm actually just going to do a few sketches of these first two, number 1 and number 2, and we're just going to look at kind of how it's getting created and what we can kind of learn from it based off what we kind of just know and are given from these first few. Looking at number 1, it's telling us specifically we just want to look at a certain interval of it. So I'm not going to graph this kind of repeated forever. I'm just going to frame it within that piece. So for this one, a little bit of freedom where we're going to put our axes. And I'm going to be putting my x-axis down the middle. But I'm going to bring my y-axis kind of off to the left a little bit, and we'll see why. So it wants it graphed from -pi/2 to 9pi/2. So before I even worry about what I need to graph, I'm going to get those intervals down. So for every single one of my tick marks here, we need to have kind of some scale, right? Some unit on it. So for me, since we want it framed within some multiple of pi/2, each of these is just going to be a pi/2. So pi/2, 2 of those gives us pi, 3pi/2, then 2 pi, 5pi/2, and so on. We'll keep working our way down. This right here before, and then we get 9pi/2. So 4 pi, then 9pi/2. So we're going to stop it no matter what, kind of at this point because of our interval. Now, equally though, we want it in the negative direction where these totally exist, right? Because these can repeat forever in both directions. So I want to make sure I get that -pi/2 on there. Now from here, I'm gonna just go ahead and kind of graph what this general shape is, but we're gonna kind of break down kind of what we're gleaming from this case compared to the originals. Now, I'm looking at cosine. So when I look above at these two cases, if you really looked, right, both these waves, the sine and the cosine on the graph, they look really similar, almost like I could just bump this guy over in one of the directions and it'd actually just be sine and vice versa. And that's absolutely true. So really the only difference is our starting point. Are we starting down on the equilibrium with sine, or are we starting up at that highest point with cosine? Well, it's cosine, so we're going to start up at that highest point. So I'm starting up at that highest point. And instead of just freehand drawing in everything, the one time kind of these 5 key points are helpful is just to measure out where that next point's going to be. Well, so for cosine, at pi over 2, we drop down to 0. At pi will be the -1, back to 0, back up to 1, 0, negative, 0, positive, and then so on and so on and so on, right? So using this method to kind of frame out where you're going to graph is going to be really helpful, and absolutely look back at your original cases just to remind yourself if you need to. You guys will get the hang of it though. Now I have most of my points, but we're also going to negative pi over 2. So this would just continue. If I'm up at the positive, that next kind of key point, I got to go down to 0. That next key point would go down to negative, then 0, then positive, and so on. So I'm going to get this little piece graphed. Start at negative pi over 2, we go up. It's cosine, so we start up at that highest point. We come down at pi, it's -1. And now if we looked even just right there, I've done one full period of this function. So we're really now just taking this, and it's just being copy and pasted, and then copy, and if we were going to keep doing it, and pasted, so on, and so on. So again, that 0 to 2 pi is our first period of it. Now I just want to look at this, because this is going to be kind of a rough idea of how we're going to approach these. When we know where our key points go, we're always finding out, we're doing cosine or sine. So do we start at the 0 on the equilibrium, or do we start up at our maximum? Then from there, we know the period is going to be 2 pi. So 2 pi away, we have to kind of end up back where we started. But there's something different on this compared to kind of the ones up above, and it's this value right here, the 2 floating out front. Now, I didn't make that note here. I did do 2 tick marks, but this isn't going up to 1 and down to -1. This is actually going up to 2 and down to -2. So just as if we were to say, have say 2x squared versus just x squared and graph them, that multiplier out front is giving us that vertical stretch happening, and it's no different here with the sine and the cosine. So moving on to number 2, again, all I did for this is I looked above, found which of the 2 cases it was, and I just tried to mimic what I saw above onto the graph. I want you guys to kind of pause and give it a try with number 2. It has 2 different graphs, however. It has one of them, which is 3 sine of x, and a separate one that's 1/3 sine of x. So to the best of your ability, again, look back up at the top, find out we're doing sine or cosine. Hint, we're doing sine, so she'll look starting at 0, 0 is roughly like this, so try to get that down and do the best of your ability. Just kind of see what happens with a vertical stretch of 3 versus 1/3, and just layer those on top of each other. And then when you unpause, we'll come back and work on it together. So hopefully you gave that a pause. And as you come back, you see I already have one of our 2 graphs down. I have that first one. So it was a sine function. So when we looked above, we knew that started on the equilibrium at 0, 0. And I started with just graphing that first period of it. So from 0 up to 3 now, because it was a 3 out front, down to -3, up to +3, down to -3, etc. And I just repeated that, and I did it up to +3 pi and down to -3 pi. So you didn't have to do all of that, but it should have started at the equilibrium, gone up to 3, we come down pi is 0, down to -3, and then at 2 pi, we end up back on that equilibrium again, that being one period of that sine graph. Now I'm going to layer on top of it this 1/3 sine of x graph. Now, the only difference between these two is just that multiplier out front. So in fact, our kind of key points should line up at the same values on the x-axis. However, instead of going up to 3, I'm only going up to 1/3. So starting on the equilibrium again at 0, 0, because it's a sine function. And instead of going up to 1/3, I'm only going, or sorry, up to 3, I'm only going up to 1/3, back to 0, negative 1/3, back to 0, up to 1/3, back to 0. And again, I'm getting just those points down first. And I'm going to do the same in that negative direction. So if I was positive 0, negative 0, positive 0, and we just flip back and forth between those two. So now I'm just going to get that graph drawn in. And I'm just going to do a dotted line kind of showing that that would continue endlessly in that direction, and then same over here. So when we're graphing it, we're clearly not going to graph everything, but it'll be kind of conventional. We get roughly 2 full periods on a graph if we can. So for here, we see we have from start to 2 pi 1 period, and we kind of only have half of it going on over here. However, we have another full period if we go in that negative direction. So enough to kind of show 2 full periods, getting that general shape down, and we can do those dotted arrows saying that's going forever left and right. So that's kind of the main way we're going to be approaching how we get the graphs down. And when you guys use WebAssign, it's going to be kind of having the graphs for you. So you'll just be pulling a lot of information from the function. Still graphing by hand, very good practice. But a lot of it will be kind of identifying the different pieces and then kind of matching that with the appropriate graph. So that's a real rough kind of dive into it. Now we're going to kind of get the standard form. So all of our functions we graph have that standard form. You're going to see how to read it, what that looks like on the graph. Coming at the top of that second page, we have the standard forms for sine and then also for cosine typed up right there. I'm just writing one out just for sine, a little bit bigger, just so we can kind of identify these different pieces. So the main thing when we're ever graphing sine and cosine is first, we need to know which function we're dealing with. And that's kind of telling us our starting point, the general shape of the graph. Does it start on the equilibrium with sine? Does it start up higher at that max value with cosine? And then we have more details from there. So looking at this, it should look actually pretty familiar. If I got rid of sine and had it be logarithm, or I had it be a squared function or a cubed function, all these standard forms kind of follow that same practice, that same method. So as we're going through, a lot of this should really be intuitive as we kind of transition into trig functions. So for example, plus and minus out front, what does that normally mean? These are our reflections, and it's no different here. Now we'll see what that looks like in terms of these trig functions and how to graph them. But if it's positive, it's exactly like we see on page 1. If it's negative, it's going to be reflected over that equilibrium. Now this value a out front, we just saw on the last page, bigger values of a goes up higher, smaller values of a, really squat graph, right, compared to 1. And we call this the amplitude. So that's what we have right here. The amplitude is just how high up you go from that equilibrium, then equally how far low you'll go in that opposite direction. Now, before we tackle the inside, which is usually the more challenging piece of graphing these, let's just touch on this lonely little guy off to the side, right? That plus d, that plus 5 or minus 8, whatever it is tacked on at the very end. These were always our vertical shifts. No different here. That just means we take that entire sine wave and move everything up, equilibrium in the curves up or down, whatever amount that would be. Now we get into the nitty-gritty of graphing this, and that's inside the function. So typically, a multiplier on the x inside the function, this is a horizontal stretch, not a vertical stretch like right here. But we don't call it a horizontal stretch with trig. this is giving us our period. So the multiplier on the x, if we divide 2 pi by it, this is giving us our period. So for a normal sine or cosine, right, we do one full kind of rotation within 2 pi. How we change that, either make it take longer or shorten that up, is by having a multiplier on that x. And again, we'll see that kind of in the first example. And then lastly, plus and minus inside, right? Those are our horizontal shifts left and right. Now, again, it's trig, a little bit different terminology. We call these phase shifts. And we find them by taking that value C and dividing it by B. And again, formulas like how to find period, how to find phase shift, that's C over B, absolutely will be at your disposal this entire time. You'll memorize it just through practice, but always nice to just kind of have this on hand. So these are all the different things we can do to a sine function. The rest of this is really kind of looking at each of the pieces separately and kind of throwing it all together at the end for some practice. So first things first, looking at number 3. And as I do number 3, I'm going to show my method of how I kind of label out everything I'm looking for and then move to my graph. And I always start with my amplitude. So how high up or down am I going to go? And since this is just a cosine, there's no multiplier, my amplitude is just 1. So just like that base case that we saw on the page 1. Next in line, I'm looking for period. And in this case, period is always 2 pi divided by b, divided by that multiplier on the x, which right here is not a 3, but it's a 1/3, right? Because this is really just cosine of 1/3 times x. So we're going to divide this by 1/3. But when you do that, you multiply by the reciprocal, and you get 6 pi. So here's what that means with this new period. Instead of it, say, being, pi, 2 pi, and we have one full rotation of cosine within that 2 pi, it's going to take from 0 to 6 pi to get that one full rotation of that cosine. It's going to stretch that cosine out horizontally. Now, after the fact, we got no reflections. We're good to go. There is no plus and minus inside, so we have no horizontal or phase shifts. And there's nothing tacked on at the end, so we have nothing vertical happening. This is just showing a change in period. So in doing so, I'm going to get this graphed out. So when it comes to these graphs, again, on the computer, it'll have things labeled, but by hand, if I were to label it how I did before, so, pi, 2 pi, 6 pi is off my page. So we get the luxury of kind of making some choice in that. So every 2 tick marks, or a tick mark, is going to be pi for us. That way I can get to 6 pi for that one full rotation. I'm going to do the same in the negative direction. And because we're stretching it horizontally, we don't need to kind of slam in a little cosine in just those 2 squares, because it's actually going to take this entire right-hand side for one full rotation. And just so we can see a little more, I'm going to say up 2 squares is going up 1 unit, down to -1. That way I can kind of see more of that curve so it's not so flattened out. Now, which function are we dealing with, right? Dealing with cosine. So take a second, even before you look on the first page, do we start on the equilibrium or do we start up at that max value? Very good. We start up at that max value. Now we have problems, right? We were jumping down. We were following unit circle. That's kind of how we were getting our points before. So what do we do now? Well, we use this period to help us graph. If I know from 0 to 6 pi, I have to end up where I started. Well, then I know where my ending point is. And then if I know that cosine has to jump from 1 to 0 to -1 and back, then I know it's going to hit -1 halfway through that. So at that 3 pi, I'm going to be down here at -1. So again, got my starting point. I go 1 period away. I have to be back at that same y value. Halfway through, I have to kind of cross over that axis. And then the halfway between the first two and the second two is where we're going to be actually crossing that axis. So how I kind of did that, where the starting points from the function we use our new period for the ending point, because that's how long it's going to take, and then you cut it in half, and then cut each of those in half, you get those 5 key points. This is how we're going to use getting those 5 key points. So I'm going to do the same in the negative direction. That way I get 2 full periods graphed on this for me. So we got our key points. Now all we do is connect the dots. So there's 1 period of cosine. This would continue. And then this also happens in the negative direction. And again, that would continue. So kind of recap on this one, because it's a really good example of how to approach these. First things first, find our amplitude. How high, how low are we going to go from that equilibrium? Second, find the period. Is it going to be just from 0 to 2 pi? Or is there going to be some kind of stretch happening? We had a stretch out to 6 pi. Now that tells us where we start. 6 pi away has to be where we end. And then in between those is a halfway point. And in between the first two is another halfway point where we cross the axis. Same with the second two. And that gives us those 5 key points to graph. And again, once you got that first period, you can copy and paste that in the negative direction and the positive direction as many times as you need. As we move down, we're going to have a little bit more of a focus now on kind of those last remaining things. We haven't touched on horizontal shifts or phase shifts, and we haven't touched on that vertical shift, which we get on that last page. So phase shifts. Phase shifts, don't let all this kind of get in your way. All this is kind of telling us is when we have a phase shift, left or right, we know 1 full period is going to be from that point, that C over B is how we find it, and then another 2 pi over B, so whatever our period is, away. And that's going to be the range for 1 full kind of rotation for us. So let's see what that looks like. Again, whenever we're going through these, I'm doing that same order. Before I even graph, I'm getting some information for myself. So first is amplitude. Amplitude is that multiplier out front. We're going to have an amplitude of 2. So we'll go up to 2, down to -2. Then from there we have period, which is 2 pi divided by b. And for us, b is just a 1 right there. So 2 pi divided by 1 is 2 pi. So no change in the period. But we do have a phase shift. So that's the C over B, or for us, pi over 2, which is our C, divided by 1, which is our B. So we have a phase shift, a horizontal shift of pi over 2. Now, just like with all the other graphing we did, when it was minus that value, we always shifted it to the right. No different here. This is going to be a shift to the right. That wraps up what we need to find from the function. Now we're going to get into graphing it. So because my period's not changing, I'm going to do the same kind of tick marks or scaling as I did on the first page, where every tick mark is going to be a pi over 2. So there's pi, 2 pi, 3 pi, and I'm going to do the same in the opposite direction. That'd be a negative pi over 2. I'm just going to write every other one. Negative 2 pi, negative 3 pi. So that is showing our period, right? We're just going to go from 0 to 2 pi originally. But we also have an amplitude of 2, so we're going to go up 2 and down 2 from the amplitude. So that's going to show us kind of the max and the min from the equilibrium. Now normally, I'm going to kind of dot this in a lighter blue. Normally, because it's a sine function, we'd start at equilibrium, we would go up to 2 and down to 0 to -2 and back to 2 pi, right? So that'd be the normal case. Now when we do a phase shift, you can almost imagine I take this original case and I tug it to the right just by that pi over 2, which is going to change our starting point to pi over 2, and it's going to move our ending point a little bit further to 5 pi over 2. However, once I know what that shift is, nothing else changes. So again, it's sine, so I'm going to start at 0, go to the max. At that next tick mark, I'm going down to 0, down to the minimum, back to 0, and I would continue that pattern. And then equally, it's going in the negative direction as well. But first, I'll kind of draw in my one full period. So that's my 1 period of sine. And then it would continue to the right. So again, from start to finish right here is 2 pi. So that's my period. Amplitude of 2, so up 2, down to -2. And it was sine, so it started on the equilibrium. So I got all my pieces there. And now again, you copy and paste and kind of fill it out. So from 0, we go -0, positive, 0, negative, 0, positive, and so on. So draw this in. And that would continue forever. So the idea of a phase shift, as we kind of saw, a really easy way to do the graphing of it if you need, is to just do a light sketch by hand of where the original would be without that shift, and then just imagine all those points that are on that blue line get shifted left or right by this value. And then again, that gives you one full rotation, and as we've seen in every case, that's always what we graph first, and then we're just filling in the rest with that rinse and repeat. So with that example of phase shift, again, that horizontal shift, we move on. We want to see an example of another different thing we haven't seen. And although this originally had a phase shift, I'm going to have you guys kind of scratch out that plus 4 pi. We'll talk about that at the end of this problem, but I just want to approach it without that plus 4 pi. So that said, let's run through our list. Amplitude, it's not -3, because reminder, amplitude is always positive. It's that absolute value of it. So it's just going to be that 3. So amplitude is going to be 3, up to 3, down to -3. Period is 2 pi divided by b. For us, that's 2 pi actually divided by 2 pi, which gives us 1, which is weird, but we'll see what that looks like. And we're going to skip that phase shift for now, but we'll talk about it. But there's one more thing I haven't touched on, and that's this negative right here. And that negative means we're going to have this be reflected. So we're going to see how to use that when we go to graphing this. So over to the graph. We have this weird period of 1. So we're not really following our normal, 0, pi over 2, pi, etc. for our notation for our scaling. We're starting at 0 every time. And then at 1, we're going to have one full rotation or one full period of this cosine function. So from here to here, I'm going to have some real tall, skinny function. And then from 1 to 2, what am I going to have? Well, I'm going to have a repeat of that, right? 2 to 3, I'm going to have a repeat of that. And then same in that negative direction. So again, our period can totally change. For this case, it's really shrinking up the period. Oops, that should be a 3. And with that shrinking of the period, that's totally fine. It's just going to change our scaling of that. So there's our period kind of giving us those tick marks. We know amplitude is going to be up to 3, down to negative 3. And then when it comes to graphing this, let's look at a few things. First is it's cosine, right? So we don't start down on the equilibrium, we actually start at our maximum. However, because of that negative out front, it's going to be flipped. It's going to be reflected. So we're actually going to start at our minimum, and that's coming from it being reflected. So that means from 0 to 1, we have to end up back at our minimum. And again, from 1 to 2, back at the minimum, 2 to 3, back at the minimum. Same if we go in that negative direction. Now, if we just looked at this one period of it, what has to happen? Well, the halfway point, we have to take the opposite value. So we have to have that maximum at 1/2. And then we have our intercepts halfway between each of those. So again, that gives us our 5 key points from that first period. And then we're just going to give that a little sketch. Now, again, that's going to happen over and over, right? So we get these multiple periods of this specific function. And again, that would continue forever. So 2 different things happening here compared to what we've seen so far. One is our period no longer includes pi, but that's totally fine. That just means from 0 to that period, whether it be a 1 or a 50, that's how long it's going to take to go from the start to the finish of 1 full rotation, 1 full period. And then we also have this reflection. So for cosine, it's easy, right? Instead of starting at the max, you start at the min from the reflection. But this is kind of a good time to also talk about what happens if it were sine. Well, if it were sine, you'd start at equilibrium and you'd go way up and down and up and down. We've seen that already. So instead of moving up first, if it were reflected for sine, you would just go down first. So take the original and you're just flipping it and marrying it. Now, before we go on to the last page for one more example and have you guys try some, I want to talk about this plus 4 pi in here. So this was technically a phase shift. So if I were to do this phase shift, it would be c divided by b, so it'd be 4 pi divided by 2 pi, which gives us 2, which means we would take our original starting place and shift it, because it's positive, to the left by 2. But here's where I kind of wanted to scratch this one out and just talk about it is, think for a second, if I took this starting point and moved it to the left by 2, would my graph look any different? Hopefully you're looking at it, and hopefully you're leaning towards no, right? If I took this starting point and then end point, right, that period of 1, and I bumped that down by 2, and then I kind of kept filling in the graph, it would just perfectly lay over it. And why is that? Well, that's because our period is just a multiple of that. Sorry, our phase is just a multiple of the period, so it's a perfect kind of bump over. So this phase shift in this case actually doesn't make any difference on our graph, so that's why I chose to leave that one out. So we'll move on to the last page, and we'll do one last thing we've not seen, and then you guys will try. Lastly on our list of all those different pieces of that standard form is we've seen the horizontal shifts, the stretches horizontally and vertically. We've seen reflections. We just haven't seen a vertical shift. So you haven't seen what happens if we move these things up or down. What does that kind of look like? So we'll do number 6 together. Again, running through that same order. Amplitude first. For us, that's an amplitude of 2. Period is next. That's 2 pi divided by b, which is the number multiplied by x, but that's 2 pi divided by 1. So 2 pi. So before I even keep going, it'll be a cosine function. So start with that shape, starting at the maximum. It'll go up to 2, down to negative 2, up to 2, down to negative 2. And it's going to be from 0 to 2 pi for that first full rotation. So it's not going to really change from that base case. So we kind of can already start to anticipate what this graph is going to look like. Now that final thing is we have a -5, but it's not in with the x, it's outside of that. So this is our now vertical shift, and this is going down 5. So what does that mean? How do we use it? Well, if we have a vertical shift, this becomes our new kind of primary thing to deal with. So let's take a look at that. So I'm going to get my coordinate system in here. I'm going to throw my x-axis way up here, and I'll just keep my y centered. Now, it's not that the graph is going to stretch, right? It's not a vertical stretch happening. We're taking the entire sine wave and we're just shifting it down. Now, we haven't seen this move yet, but we're typically, the x-axis we call the equilibrium, because that's where it kind of bounces to the max, back to 0, minimum, back to 0. We're really shifting that equilibrium down by 5. 1, 2, 3, 4, 5. And I'm just going to give a light sketch. Use this light green. Just showing this is our new kind of x-axis. This is our new equilibrium. So everything's going to be bouncing around this new line. Now, how much? Well, we see here it's an amplitude of 2. So from the new equilibrium, we need to go up 2, which is technically now at -3, and then down 2, which is down at -7. So the equilibrium comes down 5, but then we still have to maintain that amplitude of 2 about that equilibrium. Now we finish out the rest. Normal period. So when that was the case, every tick mark was a pi over 2 for me, so I'm just going to maintain that. I'll do that in the positive and negative direction. And now we go in for graphing. We start with cosine. Now cosine is not starting at the equilibrium, it starts at our maximum. So our maximum is 2 up from that equilibrium. So that's our first point. 2 pi away is going to be our end point. So there's 2 of our 5 key points. Halfway between those for cosine, it has to hit the minimum. And in the first half, it crosses here. So there's the 4th key point. And then on the way back up, it'll have to cross here one more time, giving us our 5th key point. So for our first full period of our function of our 2 cosine of x minus 5, that's what it's looking like right there. And then again, we could continue this, right? This would continue down and go on forever. And we're having the same thing happen in that negative direction. And this is why it's nice to kind of graph that first period, because we know exactly where those points should go and what increments, so it makes it really easy to kind of rinse and repeat on that. So that kind of wraps up our final piece of what could happen to these two functions when we graph it, is that vertical shift, and that shifts the equilibrium, and thus kind of where those amplitudes go from there as a whole. So we got 2 more, number 7 and number 8. I'm going to have you guys give these a try. When you come back, they'll be done. We'll kind of talk about it. And again, follow that same flow. Talk about amplitude, find the period, any shifts. Now for 7, it's got the grid for you. And for number 8, it doesn't. So take a moment and just kind of look at number 8 and identify maybe some of the things before I let you guys loose on that one. So take a minute, look at number 8. I'm just going to kind of look through it. I got a negative on it, so we got reflections. There's nothing on the x, so my 0 to 2 pi will be my period. There is something added inside, so I should see some horizontal shifting, some phase shifting. Then I see this extra +3, so stuff should be going up or down. Hence, that grid, or that the axes, sorry, aren't there for you yet. So keep that in mind. Give it a pause. Give number 7 and 8 a try. When you come back, we'll see how you did. So hopefully you gave 7 and 8 a try. As you come back, take a look at it. I only graphed the first period of it just to kind of see, and we'll kind of fill in the rest together. For number 7, we have that amplitude of 2 from the out front. Our period is 2 pi divided by b, so 2 pi divided by 3 pi, so 2/3. So as we see on this graph, this little light blue line I did from 0 to 2/3 would have been what that graph looked like from 0 to 2/3. However, we had a phase shift, and we get that from the c divided by b, and it shifted it also 2/3. Now, as we saw on that second page, I had you leave out that phase shift because we saw it didn't make a difference to the actual graph if that was a multiple of that period. And lo and behold, these are multiples of each other. And as we look at what that phase shift would be, so starting out at 2/3 and then go 2/3 more past that, you see it actually lines up perfectly with the original case before it. And again, that would continue forever. So kind of another case, wink, wink, right, where the phase shift and periods were multiples, and we see that that phase shift didn't actually physically change what the graph looked like as a whole, it just changed where we started it. Now, moving down to number 8, a couple things. We have amplitude of 1. We have period as 2 pi over 1 from b being 1, so the period's totally normal, hence the, each check mark being just a multiple of pi over 2, like a lot of the others. Our phase shift is c divided by b, which is just pi. So we're taking our entire graph and we're shifting it over by pi. And then we're also reflecting it. So a couple things happening on this one, right? So when I got my original 5 points, well, I knew it didn't start at technically 0, right? Because it went pi away. So technically, it should have started here at pi, which means 2 pi away would have been our endpoint. But it would have been reflected. So instead of going up first and then down, it is actually going to go down and then up. But lo and behold, we see that's actually no different than if we only did one of those two, right? So again, something weird happening between now the phase and reflection that we'll kind of dive into in the next section is these are kind of undoing each other. So instead of it going up from that first point because it's reflected, we see all that really happened is we had that phase shift, which doesn't change it. And then that same direction forever. So there will be times, which is why I had you guys try the last two, where even though there is that shift, all of this is there. It's just changing where we're putting that first initial period down on the graph. But if you looked at the graph of this as a whole, and then you graphed it one more time without that reflection or phase shift, it would look the exact same. So there are going to be times where some of this stuff might kind of undo the change of another. So that's cosine and sine. We're going to see the other 4 trig functions in 4.0.